Hi, my name is Neil Forcier. Welcome to the General Purpose Electronic Test Equipment blog, or GPD blog for short. In this video blog post, I'm going to be talking about using a feature found on modern day frequency counters known as gapless sampling, and how you can use gapless sampling to analyze noise close in to a carrier frequency. So whether you're working with a clock signal, a high-speed digital signal, or a communication signal, tools such as a spectrum analyzer and scope are great for analyzing those signals, and every engineer has one or both of these instruments on their bench. But they also can't give you insight into the noise that's very close to the carrier. Modern day counters, and of course we know frequency counters to be devices that give us very high accuracy frequency and high resolution frequency and timing measurements. But using this gapless sampling feature, we can actually look at noise very close to the carrier. Now, what is gapless sampling? So the way a counter works is it measures frequency or timing events by triggering off an edge, or capturing an edge event and then capturing another one and returning that time. Gapless sampling means it continually catch or capture edges one after another without rearming or without taking a break. So you're getting a complete picture of a signal without skipping any parts of that signal. Okay, I'm going to do a quick example. Now, gapless sampling, what can it be used for when I say analyzing noise close into the carrier? It can be used for modulation domain analysis, which is I'm going to show you here today. It can also be used for doing true Allen variance measurements. It could also be used as a very low-cost solution for analyzing phase noise. Okay, so I'm going to do a quick demonstration of using gapless sampling to do modulation domain analysis. And for those of you who are not familiar with modulation domain analysis, if we know a scope is used to look at a signal in the time domain, amplitude and time domain. A spectrum analyzer lets us look at a signal in the frequency and power domain. Modulation domain analysis gives us frequency on the y-axis and time on the x-axis. Okay, so I have 4 instruments here. I have Agilent's new 53230A universal counter, which of course does all the normal measurements that one would expect from a counter, but also has gapless sampling up to 1 megasamples per second. I have a scope, I have a signal analyzer or spectrum analyzer, and sort of hidden underneath my counter, and I apologize if this is not showing up well in the video, I have a function generator. So the function generator is going to serve as our DUT, and what I have is a 10 megahertz sine wave coming out of the function generator, but I have modulated that signal, FM modulated that signal, that 10 megahertz sine wave, with a square wave. But the FM modulation deviation setting is only set for 3 hertz. So our signal is only going to deviate 3 hertz from our center carrier frequency, which is 10 megahertz. So let's look at what each instrument is reading right now with this current signal. We can see in our scope our 10 megahertz sine wave, and you can't really tell at all if there's any noise or anything going on. It looks like a clean 10 megahertz sine wave. We can see on our signal analyzer or spectrum analyzer that there is some type of noise close to the carrier. I have the span set low, but it's hard to tell what the source or what form that noise is in to give us any clues of what might be causing that noise. Okay, so now I'm going to do a quick modulation domain analysis using the gapless sampling feature from the counter. I wrote a simple program that's going to connect to the counter, grab 10,000 gapless samples, and display them in modulation domain analysis format. So here we go. And there we go. We can see our FM modulated square wave that's real close to our carrier. Remember, the square wave, the FM modulation is only set for 3 hertz deviation from the carrier. So, we saw in the spectrum analyzer that there was some noise on our signal, but when we get a much clearer picture of the noise, like this, it helps us determine the source of the noise. Okay, so that was just a quick demonstration of how we could use the gapless sampling capability found on modern day frequency counters like the 53230A to look at noise close to a carrier. Thanks for watching. If you have any questions about what I just showed you in the video, feel free to email me. If you're watching this video from the blog, embedded in the blog, my email address should be up above me, I believe, or to the left of me. One of those. Anyway, thanks for watching.